All right, we spent a good amount of time on polynomials, but we really didn't do anything with polynomial inequalities. So I want to make sure we look at that. So that's what this lesson's going to be on. And so we're going to just go through a bunch of examples. The first one, it says solve the inequality, express the answer in interval notation. So the idea is with an inequality, you're dealing with like greater than, less than, greater than or equal to, less than or equal to. And when you have polynomials that are more complicated than just like a regular linear equation, there's probably going to be different parts of the polynomial that are less than or greater than whatever you're dealing with. And for all these examples and for this assignment, we're going to focus on polynomials that are less than, greater than, less than or equal to, greater than or equal to 0. Because usually when you're dealing with polynomials, you usually get everything on one side of the equation, and so that the other side of the equation is just 0. And that's what you do to be able to identify the roots and other properties of the polynomial. So this first example, this has been factored already. This is in factored form. We have x minus 6 and x plus 2. And the first thing I want to do is look at what kind of polynomial is this. So you don't have to do FOIL and multiply the whole thing out, but you do want to imagine that if you did, you would have an x here and an x here. Those would get multiplied together and you would get an x squared. So that means you have a second degree polynomial. And if you remember back to when we were doing polynomials, second degree is a parabola. So whenever you have x squared, you have a parabola. The next thing you want to do is identify the roots or the zeros of your polynomial. So the way you do that is by taking your factors and setting them equal to 0. So we're going to say x minus 6 equals 0 and x plus 2 equals 0 and solve both of these little equations to figure out what values of x would make this polynomial equal to 0. So when we solve these, we're going to get x equals positive 6 and we're going to get x equals negative 2. So if you think about what the graph of the equation, if this was x minus 6 times x plus 2 equals 0, and you graph that equation, the function would have would hit the x-axis, would have a root or a 0 at 6 and at negative 2. And it would be a parabola. So it's going to look like something like this. That's what the graph looks like. And so when you look at the graph, what we're trying to do is to figure out where is this function going to be greater than 0. And we can see it's greater than 0 right here on the left side once we get past negative 2. And it's greater than 0 over here on the right side once we get past positive 6. So the way we're going to write our answer for this is we are going to say that x minus 6 and x times x plus 2 is greater than 0 when we are from negative infinity up to negative 2 and when we are from positive 6 up to infinity. Notice I use all parentheses here because this is just greater than. It's not greater than or equal to. So this is going to be our answer in interval notation. All right, next example here. We're going to do the same thing. We are going to figure out what degree it is. This, again, is second degree. We would have an x squared if we multiplied this out. So it's going to be another parabola. We're going to find our zeros or our roots, and rather than working these out, we'll just kind of take the shortcut. If we have x plus 3, we know it's going to be x equals negative 3. If we have x minus 7, we know it's going to be x equals positive 7. So we'll just change the signs there. And we'll do another rough sketch of our graph. So we're going to have a parabola that hits the x-axis at negative 3 and at positive 7. Doesn't have to be pretty, you just have to get the idea of what it would look like. And so this time we're doing less than or equal to 0. So we want to know where is this function going to be equal to 0 or less than 0. So this time it's going to be this middle section. from when it hits at -3 over to where it hits at +7. So it's going to be only going to be one interval. And this time we've got to use the brackets because this time we are including the place where it's equal to 0 because it's less than or equal to. So we're going to go from -3 to +7 to indicate this section of the graph right here where it hits the x-axis and dips below it. That's where it's going to be less than or equal to 0. And that's going to be our interval from -3 to +7. So you're identifying the zeros, using those to visualize the graph, and then looking at the graph to see where is this going to be greater than 0 or less than 0 or equal to 0. All right. Same idea on this one, except this one's not factored. So we have to factor it first. So what I'm going to do is I got to come up with two numbers that would multiply to give me +5 and add to give me -6. The only way this is going to work is if they're both negative, because negative times a negative would give me a positive. Negative plus a negative would give me a negative. And the only two numbers that are going to work are going to be 5 and 1. So we have x minus 5 times x minus 1, and this is less than 0. So again, I'm gonna identify this as a second degree polynomial. So another parabola. I'm going to identify my zeros or my roots. This time it's at +5 and +1. I'm going to do a rough sketch of my graph. So we have +1 and +5. And so my parabola is going to come down here, go back up through here. And I'm looking for less than. So less than is when is it below the x-axis? When is it negative? And it's going to start at +1, and it's going to come back up at +5. And because it's less than, I'm going to use parentheses because I don't have an equal to this time. So that's going to be my interval. That's going to be my answer for this one. It's going to be from 1 to 5. All right, another one, this factors 2, and this is going to be a special case where something weird happens. So I'm going to make my two parentheses and put my x here. Again, I'm going to have minuses with both of them. And the number I'm going to end up using is 4, and I'm going to use it twice because 4 times 4 gives me 16. 4 plus 4 gives me 8. So it's going to be x minus 4 times x minus 4. I could rewrite that as x minus 4 squared. And so again, I promise there will be some of these that are not just second degree, but this is another second degree. It's another parabola. And here, my only root, if I were to set these equal to 0 and solve, my only root's going to be x equals 4. But I have two different factors that give me that. I have two x minus 4s that both give me this +4. So this is what's called a double root. And when you have a double root, what's going to happen on the graph is the graph is going to just hit that number and then bounce right back up. So what I mean by that is let's go ahead and put a point at 4, at +4. And so this is a parabola. It's going to come down, and instead of dipping below the line, and this is a very bad parabola. I'm going to take another stab at that. That does not look like a parabola at all. These are a little harder to draw when they do this. Instead of crossing the x-axis, it's going to just graze the x-axis and bounce back up. So it only hits the x-axis in one point. So here, what it's asking us is, where is this greater than 0? Well, this is greater than 0 everywhere except when x is equal to 4. Because when x is equal to 4, it actually touches the x-axis. And it is equal to 0. Everywhere else, it's greater than 0. So what we're going to say is from -infinity until we hit 4, we're good. And then after we hit 4 up to +infinity, we are still good. So that's going to be our interval on this example. It's everything except for 4. All right, here, as promised, is one that's not second degree. So if you look closely at this, you have x minus 3 squared. So that's going to square the x. And then that x is going to get multiplied by another x. So if we were to multiply this whole thing out, our first term would be x to the third. So this is a third degree polynomial. It's a cubic. Now, normally we're going to have 3 roots, but if you'll notice here, we have another double root. We have x minus 3 squared. So we could think of this as like x minus 3 times x minus 3 times x plus 2. But when we work it out, we're only going to have 2 roots. We're going to have x equals 3, and we're going to have x equals negative 2. So I'm going to sketch out the graph, and this one's going to look a little different because it's third degree. It's cubic. So I'm going to put my point at negative 2. I'm going to put my point at positive 3. And so if you remember cubic, that comes up from the bottom through this point. It's going to go up like this. It's going to come back down. Now, here's the thing. This is a double root here at 3. So instead of crossing back below the x-axis, it's going to do what we did last time. It's going to graze it and go up. So this only happens when you have something squared and you have a double root. That's when you get these curves that just hit the x-axis and go right back. And that is a very poor drawing, but it's enough to know where everything is less than, greater than, or equal to 0. And that's what we need. So for this problem, we want to know where is this graph less than or equal to 0. And so we're looking at it, and it looks like the only place that's really less than 0 is here on the left side. And so we're going to say from negative infinity until we get to negative 2, we are less than or equal to 0. So we're going to use a bracket to say that negative 2 is included because we can be equal to 0. But we also have this double root at 3. So that's one other place where it's equal to 0 because it's less than or equal to. So if it's equal to, that still counts. So here's how we write that because it's only one number. When you only have one number that works on an interval, when the interval consists of one number only, you use the fancy brackets. And you put that number in there. And that means 3 and 3 only is what's included right there. So that's what you do sometimes when you have these double roots and you have these points that stand alone, like it's the only point in the interval. That's how you write it, with just the single number and the fancy brackets. So another thing really quick, because you spend a lot of time on parabolas throughout your math career in high school. We don't spend as much time on cubics, but every cubic is going to follow the same basic idea where it comes up, goes back down, goes up again. So they're all going to follow that same basic pattern. And again, you don't need to know exactly where it goes. You just need to know where it crosses the x-axis, where it's greater than 0, where it's less than 0, and where it's equal to 0. Couple more. This one's a lot bigger. We've got a lot going on here. This is actually a 4th degree polynomial because if you look at this, we have an x. We have an x that's going to get squared, and then we got another x. And if you put all those together, you would get x to the 4th. So this is a 4th degree polynomial. And we have 3 roots. We have x equals negative 5. We have x equals negative 1, and that's a double root because there would be 2 different factors that give us that because it is squared. And then we have x equals positive 3. And then we want this to be less than or equal to 0. Now I'm going to sketch the graph, and here's an important thing to know as we get into higher degree polynomials. Whenever your degree is an even number, then your standard graph is going to start at the top, come down, and end up going back up. Whenever you have an odd number, it will start on the bottom, it will do stuff, and then it will end up going up. So even is going to be like this type of situation. Odd is going to be like this type of situation. So this is even. This is fourth degree. So let's put our roots on here. We have one at -5. We have one at -1, or technically have two at -1. And we have one at +3. So this is even. It's going to start off here, hit that point. It's going to come up to -1, but it's only going to graze it. It's not going to cross the x-axis because this is a double root. And whenever it's a double root, it just hits it and goes back. And then it's going to come up through 3. So it's going to be like this W-looking thing. And we want to know, where is it less than or equal to 0? So if you look at this, it starts out greater than 0. Once you hit -5, then you are equal to 0, and then it goes less than. And you stay less than until you get to -1. But when you hit -1, it's still equal to 0. So that still counts, and then it keeps going all the way until you get to 3. So from -5 all the way to +3, you are less than or equal to 0. And then after +3, it goes greater than 0 again. So your interval here, it's just going to be one big interval from -5 to +3. Even though all that stuff's going on in the meantime, it stays less than or equal to 0 the whole time. Last one. I wanted to do this one. There's not one like this on your assignment, but I wanted to do one just in case it comes up somewhere. This is a third degree polynomial. You have 3 x's. But the thing that's different about it is you have this negative sign out front. And what that negative sign is going to do is it's going to switch the direction. So really quick, if you have a negative sign out front, if the whole function's being multiplied by the negative, then your even numbered functions, your even degree, would flip upside down. Your odd are going to flip backwards. So instead of coming up on the left side and then going to the right side, they would go up on the right side and then end up going to the left side. So it's kind of like a positive negative slope type thing. So this is going to go backwards. It's going to go the other direction. But it is third degree. And we don't have any double roots this time, so that's nice. We just have 3 regular roots. We have x equals 1, we have x equals -4, and we have x equals -2. Again, just a reminder, because I've been kind of rushing through this part, all I'm doing to find the roots is taking each of these factors, setting them equal to 0, and then solving for x. But what it always amounts to is just changing the sign. All right, rough sketch of a graph again. I'm at -4, -2, and +1. -4, -2, +1. But this is backwards. I'm coming from the other direction this time because I got that negative out front. So it's going to go like this. It's going to hit. Did not hit that very well, but it's going to look something like this. It comes up from the opposite direction, passes through the first point, hits a peak, goes down, passes to the second point, hits a low point, comes up, goes back through the third point. We want to know where it's less than 0. And there's 2 intervals here where it's going to be less than 0. It's less than 0 right here in between -4 and -2. And because it's just regular old less than, we're going to use our parentheses. And then there's one more interval. It goes less than on this side as well. After you go past +1. I'm going to erase this so I have a little more room. All right, sorry about that. So we have from -4 to -2 again. And then the other interval is after it hits 1 and then goes off to positive infinity. So those are going to be the intervals on which it is less than 0. So that's polynomial inequalities. The actual working stuff out is pretty easy. All you're doing is setting things equal to 0 and really just changing signs. The trick is being able to visualize the graphs. And you don't have to, all you really need to know about the graphs again is where are the roots? Where does it hit the x-axis? Where is it going to be above the x-axis? Where is it going to be below the x-axis? You don't really need to know maximums or minimums or y-intercepts or any of that other stuff. Just where is it greater than 0, where is it less than 0, and where is it equal to 0. So that is polynomial inequalities.